Just give me a moment. I'll just come. Just 2 minutes. Yeah, we'll get started. Oh, just a minute. So, are you guys informed about the exams?
Yes, sir.
When is it? When is it scheduled?
Tomorrow is scheduled after the class. Good evening, sir.
Hey, good evening. Okay, sir.
Tomorrow morning 11:30 it is scheduled, sir. Please.
Tomorrow morning 11:30. Okay.
11:30. I think after our class, like 9 to 10:30.
Yeah, that's what I said. Like after the class, if you continue for the exam, then you will finish that work and then you can move on to the next work. That's what I said.
Yeah, that's correct. Just a half an hour gap is there.
Yeah, I think you can brush up. You can prepare in between that. So
Yeah,
I
yeah.
actually wanted to tell you a few important topics also that you can quickly brush up. Okay, tomorrow maybe today or tomorrow I'll try to tell you. I think if I tell you today, it will be ideal. So
That's
questions. Yeah, the questions are a little bit. Some of the questions are a little bit will make you think. Okay, to confuse you. So I wanted everyone to. I'm going to tell you, okay, which are like there will be little tricky questions. Not all the questions are tricky, but few questions I have purposefully meant it like purposefully I have done it a little bit tricky so that I wanted to know the what do you say, like the analytical skills that is there inside you. Okay, so I'll just give you some. By today's class, I'll give you. Okay, so to continue from the last class, can anyone summarize what all I said in the last class about we were talking about the multivity and all, right? Can anyone continuation say for you to get the momentum and move on? Anyone can say?
I think we discussed about these multi-voltage components and the communication between them and how the level shifters would work and all that stuff, sir.
Okay, so
High level.
yeah, you just said it in a very high level. So 1 minute, let me share the screen. So we'll just fastly, just 2 minutes, we'll run through. Okay. We were talking about different low power methods. Okay. In that first one is the clock gating. Clock gating can be done at the design level, but nowadays it is being done at the tool. Tool takes care of doing it. So where the clock signal is only given to a network if there is any functionally, if there's something happening, then only the clock goes into. Else the clock doesn't goes into the into those modules. So by then you are actually saving the switching power and so basically there is a little amount of power that you're saving it. So and then you. So nowadays the tool has the capability to understand the clock gating cells that are part of the library PDK. So you have to mention in your synthesis script to enable the clock gating. So when you enable, it will ask for like to how many how many flip flops range you want to insert the clock gating cells. As in for every 1,000. Products here is you know what clock gating cell does, and second is with the help of the synthesis tool, you enable clock gating while doing synthesis. So these are the two learnings out of this. Okay, and then you have the voltage using the supply voltage. We have multiple supply voltages you can pick up and use. This kind of approach can be used if your design has multiple supply voltages. For example, you have in your design you have a CPU and then you have a cache unit. In that case, the cache will work at say 1.9 volts. So if you have multiple supply voltages like this, depending upon the requirement, the cache might work in a higher frequency, and that's why you are giving higher supply voltages. So like this, you have multiple operating voltages. So that means what? You will have different types of standard cells. You have multiple operating voltage standard cells. It will be there in the as part of the PDK. I mean, this is all same technology. In same technology already, you will have multiple operating voltages. So to communicate, if you have the communication between all these three, then you need between the voltage domains. If you want to communicate, you need level shifters. Okay, and so while you are doing all these things, when you are implementing it as part of your physical design, as part of the physical design engineer, what you take away from here is, see, you will be given that this block works at 1.2 volt, this works at 0.9 volt. That's what it will be given to you, but you can't change that. But what you can do is at your implementation, how do you implement? That is in your freedom. So you implement in such a and typical. You also have different VT, as part of the standard cells. You have low VT, high VT, and standard VT cells. These also will be given to you. Okay. As I said, if you on the VT that you are required with. Okay, so most of the companies will make you to work with the nominal VT only, standard VT. Depending upon the requirement, if they are budgeting with respect to power, you will choose a particular VT. If they are budgeting with respect to the performance, you will choose a particular VT. Okay. Then you have level shifters. Yeah, as I was saying, to communicate between one domain to another voltage domain, the signal has to be translated accordingly. So you have level shifters. Either if you want to have level shifters between high voltage domain to low voltage domain, this is the example that I have demonstrated you. And if you wanted to have a level shifters from low voltage domain to high voltage domain, then you will also tell the level shifter about the information of the source voltage, source power domain. That's the lowest power domain. About that, you will have to connect a wire and give that as a reference to the level shifter cell. Okay, so yeah, these are certain recommendations that I have told you. Issues that I was telling you is while doing STA, the clock generation is there not, that has to go and supply the entire clock network for 2 different voltages. It will be a very big challenge. Okay, so yeah, I told about DVFS also. I hope that is clear. We started with the SVS, and then we went to MVS, and then to DVFS, and then we went to AVS. Okay. So today, what we will do is so all these things I said, right? All these power constraints, that is all these power constraints that I showed you, right? All that when you are implementing it, how do you implement it? Like I wanted to say my power domain, that I want to create one power domain for my cache module, one power domain for my CPU. Any idea I told about this, right? You remember? How do you communicate to the tool about this? Like if you want to tell that I wanted to give supply voltage for my CPU as 0.9 volt, and I want to give my supply voltage for my cache modules as 1.2 volt, and the corresponding cells has to be chosen, right? So you will have to guide the tool to pick up the corresponding cells, right? So how do you tell that? How do you tell the tool? You will have to guide the tool by asking the tool to choose the corresponding cells, correct? How do you tell the tool?
It's some UPF kind of thing.
Exactly, very good. It's UPF constraints that you have to give. Very good. So UPF. So we will see a little bit about UPF and some commands that are there in this. I mean, some important commands, not all we will cover, but some of the important basic commands that is part of this UPF. UPF is
unified power format.
Yeah, unified power format. So this is basically basically the constraints. It is the power constraints that you give to the tool. Like you have timing constraints, you will have the power constraints, which will talk about my this will talk about my supply voltages. VTs. This talks about my power switches. This talks about my level shifters. Yeah, mostly this only. So we'll see if I have left anything. We'll cover it on the go. So basically, the power constraints will include about all these things. Like if I have a block, if I have a block here, say V1, which works at 0.9 volt, and V2, which works at 1.1 volt, and this is 1.2 volt. Now so this is say V3. Now this I have to tell it to the tool, right? So my V1 module is will have to pick up all the cells, that is pick up a so 0.9 volt is going to be my VDD, right? Then it has to pick 1.1 volt VDD cells and 1.2 volt VDD cells. Right? Now, there will be set of library.lib library. The .lib will be there for 1.1 volt, 1.2 volt, and 0.9 volt. You will be able to see all these cells. Okay. So you will have to point all the .lib and the corresponding models that are available. You'll have to point for 0.9 if you have to point for block 1. So block 1 means what? It is a So you will have a module, right? You in Verilog, when you're writing the code, you will have different sub modules, right? So my B1 will be another one module that is separately synthesized, and then you will have the complete physical design implementation for B1 separate. Similarly for B2 and B3. Okay. So if I want to come, if there are some set of signals that talks between B1 and B2, then you will have a level shifter here. Okay. So that level shifter cells and all has to be placed inside which module? Should I place it in B2 or B1? All these decisions has to be taken well in advance and has to be formatted inside this UPF file. Okay. Okay, so some set of basic commands. Let's start with okay, let's start with this command: create underscore power underscore switch. Okay, so what is this command? The purpose of this command is it defines a switch in the power domain. So what is the purpose of a switch? Do you guys remember when I was taking in last class? Anyone can say about this switch?
So on and off.
Yeah, switch purpose is on and off. I understand, but what is that does? For example, you have a Mac unit here and you have a vector processing unit. No, so block A and block B. What does
Whenever the Mac processor unit is working, then that
good
like that.
Good. So through this power gating controller, the decision is taken. Whenever it is required, you turn it on, else you turn it off. So how do you do it inside the I mean, you wanted to do this. So for doing this only, you need special cells, right? So you will have which place you have to put the switch for module A, and which place you have to put the switch for say block B or module B. What you have to I mean, all this has to be conveyed to the tool. So this create power switch command does that. So it basically it will insert the switch in the corresponding power domain. Okay. So this switch has multiple flags, like flags as in. So basically, you will have to tell here the what you have to tell here is the port name and the supply net name. This is so port name and supply net name is this output supply port of the switch and the net where this port actually connects to. Okay, so there you will have to tell the here. So so you have input supplies like this, and these things has to be given for this command, and the tool gets the information from these flags only. Okay, any doubts? You're able to relate, right? You're able to relate what I'm saying with respect to the tool implementation.
Yes, sir.
Okay. So you have like this lot of, I mean, there are a couple of other flags also, but as of now, you just remember these are the main flags. Other flags are like depending upon the usage only. If required, you can use those flags. Now this is one command, and one more command is so this is create supply underscore net. See, I'm just picking up these commands from a script, okay, that we used long back for one project to create this UPF. So I'm just picking up which all can be told to you. So these are some basic commands. Okay, so create supply net. Basically, this create power or ground supply nets. It's called hyphen. You have domain name. Basically, this will tell you which is it 1.1 volt or 1 volt, 1.1 volt, on which power domain you want to create this net. That net could be either a power net or a ground net. Okay, but you on what voltage domain it has to get created, that has to be told. Okay, and also you give the net name also, hyphen net name. So that net name for want to create a port. See, creating a port means you cannot create a port for functional utility. So this is for power utility. So if you are going to create a port for functional requirement, then the functionality of the design you are trying to change. Okay, but what you are doing just for fulfilling the power requirement, you wanted to create a port wherever applicable. So for creating the power, for creating that port, this is a command that you can use it for. And then also this has hyphen domain, on which domain you want to create the port. And also there is one more thing is direction. So obviously when you're creating a port, it should be in or out. So you have to declare that. Okay. So domain hyphen domain will be the domain name, which on what voltage domain you want to create this port. What else? Then about level shifter. If you want to want to just specify the level shifters, so you have to give set underscore level underscore shifter. Okay. So what does this command do? This command specifies a level shifter, strategy. So in what way you want to use this level shifter? This command will do. So obviously, yeah, this will have another the flag, which is like on the domain, on which domain you want to create the level shifter. You have to give the domain name by giving -domain. Then you have to give elements. So basically, sorry, to give different elements list. In this elements list is you have to it is the list of design elements, pins, ports, or nets. Okay, to which this particular set level shifter has to get applied. So basically, this comprises of the list of design elements. As in design elements means what? Which block? Okay, which block this has to go, and in that which pins, ports, or nets to which the strategy is applied. The strategy means, I mean, when you're setting a level shift, set level underscore shifter, right? This particular set level shifter command, for in that, what all elements does that include? Okay, and you will have to also, there is another important command which is hyphen applies underscore to. Okay, so this is, so what does this hyphen applies to say is key whether the domains input ports, output ports, or inouts are level shifted. Okay, level shifted means from one low voltage to high voltage or high voltage to low voltage, whether it is shifted, you will have to say all the input ports are level shifted or the output ports are level shifted. So you have to specify only if inputs are level shifted, you have to specify inputs, or if it is outputs, you have to specify outputs, or both inputs and outputs means you have to specify it as both. So you have to mention inputs or outputs or both inputs and outputs in this, and that corresponding module is level shifted. So that you have to say using this flag hyphen applies underscore to. Low to high or high to low or both. So what you're doing is you're just mentioning here this particular, see, you're telling that this particular domain name, in this particular domain name, you are also mentioning this domain name will comprise of all these elements. Ports, everything you're mentioning in this element list, and also you're saying which all it has to applies to. Then you're setting the rule also, like which kind of level shifter cells has to be used. All these things you are telling it in the okay, most of the flags I have mentioned for set level shifter. There is one more important thing. Set underscore retention. See, when you remember about retention cells, which I was telling?
Retention cells are when you shut off a power domain, it's used to hold on to the necessary data which needs to be saved when you turn back the power on.
Yeah, very good. So yeah, so that in the last class I was mentioning about that, right? So you will have to tell that also in the power constraint, so that the tools pick the corresponding the required retention cells. So set underscore retention is the command that does. So what does this do? This specify which registers and set the save and restore signals for the retention functionality. Okay. So this set retention, when you're giving, yeah, obviously one flag, default flag is always the domain, which you specify the domain name. Then hyphen retention hyphen underscore power underscore net. So you have to specify the net name where the where this retention registers are inferred. Okay. Then element list. So you have to specify the list of list of objects in this power domain. List of objects in the power domain. That is the design elements. Yeah, and then you have the sequential. Signal names to which this strategy is applied. Okay. So basically so you're going to preserve the value, right? So either you're going to store 1 if it succeeds or 0 if it fails. That's all. Okay. So these retention shells will hold that value when that particular module is powered off, and that will be that value will be used when that gets turned on again. There will be a retention control, okay, that will happen by using while you have to perform the save and restore. So all these things, the tool will help you to implement those required, how do I say, those required save and restore signals. All those tool will try to implement those and will perform the operations. Like operations as in when those signals when it has to be saved. So basically, there are some control signals, okay, and what do I say, some assertions, okay, for that will be needed for this retention strategy, okay. So yeah, so let's stop here for the retention cells. If there is any hands-on that could be done for this, I will be able to. I'll try to find out something, and I'll be able to give you when you're coming for hands-on. No, I'll try to show some things, because more theory on this is not anyway going to be useful. If I can demonstrate something using this, then it will be useful. Okay. Yeah, I think that is all. Just a minute, I'll have some water. Just yeah. Yeah, any doubt? Anything on this power? So we'll close this related to this UPF, all those low power voltage domains, all those things. We will close it here. Any doubts? Any clarification? Okay. Okay. So next we will move on to FinFET, as the meeting link today says about that, right? Today we are about to discuss about FinFET. Okay. So FinFET is what I would say is a great change that happened, okay, on the design of the on the basic structure of the transistor itself. So in okay. So there is structurally one difference that is there between these two fellows. Okay. One major this fellow is a 2D planar design. 2D, sorry. 2D planar design. This fellow is a 3D planar design. Okay. Maybe I'll try to get an image for this. One minute. Yeah. Is the screen visible?
Yes, sir.
So what is that FDSY?
I'll come to that.
Okay.
Okay, so see, as I was mentioning, there is a structural difference, important structural difference between between CMOS and FinFET. Okay, if you see this diagram, the first one is a CMOS, where you have the source, drain, and the gate. Okay, but if you see on a FinFET, which is this, that does also has a gate, but you see the channel in the between the source and the drain. You have the channel that comes out of the existing CMOS. Okay, it is coming out as a fin. Fin means what? Basically, there you know it. Fishes have the fins to swim, right? That you say that those are the wings for the fishes, right? So that similarly, you have this fin that comes out of the existing CMOS. Okay, the channel comes out here, and then there's a gate. The gate is surrounded across this. Okay, so what is this has given an advantage is, okay, when you are moving to a lower nodes. Yeah, before saying that, let me tell you, the CMOS technology is only applicable until 28 nanometer. I would say about 28 nanometer process technology, about 28 nanometer, 28, 40, 45, 55, 60, 90, everything. So when the channel length is shrinking, then automatically there is this there is an evolution that has to happen in the design of the CMOS. Okay, that is what is incurred. So what is this? The main advantage, I would say, just a minute. The main advantage, 1 minute. It's getting handy. Just a minute. Just a minute. My system is hanging. Just a Okay, yeah. I think now I'm able to control. Okay. So yeah, I was telling about the when the technology of short channel effects on a CMOS. This is something fundamental. Us full control over the channel, because when this particular fellow is shrinking, the source and the drain, when it is coming closer here and this channel length is shrinking, okay, then this particular gate will have very less effect, correct? So for that only, to overcome that short channel effect only, there is a change in the design itself, this using of FinFET. Okay, is it clear? Is it clear? Is it clear, Rohan?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. Okay, so these are basically some unwanted effects. Okay, thanks, Rohan. These are some unwanted effects in MOSFETs when the base and reducing the gate control. Okay, this kind of to overcome this only, this kind of FinFET technology they made, where the gate is elongated and it comes out as a fin. Okay, through this technology, the short channel effects are overcome. Okay. And there is one more thing also. Maybe I think when you look into the fundamentals, you will be able to see that there is in CMOS technology there is high amount of leakage current. Okay, when the technology shrinks, when if you're keeping on using the CMOS technology, there will be high leakage current. Because of that, also we are moving to this FinFET. Okay. Just a minute. And the advanced version after FinFET, so one technology that I have worked on is this Intel's 22 nanometer that I have worked on early days. So that technology is a FinFET technology. I mean, it is a FinFET with FDSOI. FDSOI is basically it's called fully depleted silicon on insulator. Okay, so this technology is an advanced version of FinFET, where you have the source and the drain raised like this. Okay, another structural change only. If you have another source and drain, it is raised, and basically you will not be having this fin anymore. You're basically like here the gate is raised through this fin. Here the gate stays like that, and only the source and the drain is raised. Okay, so you can have combination of these two technologies, FinFET, FinFDSO, SOI can be. I mean, you will be. You can. I mean, you have these kind of components where you will have FinFET plus FDSOI. Okay. I mean, there is a theory that says that FDSOI is something like a CMOS only. If you see, it looks very similar to CMOS, right? So there is an just the difference between both of them is you have a bauxite layer. That's all. Bauxite is this layer. There is a between silicon substrate and the source, drain, and gate. You have one more layer. Okay. This bauxite. Sorry. There is a buried. This layer is called buried layer. This buried layer is getting sandwiched between these two. So there is one theory that says this is an advanced version from CMOS. It got evolved, and this FDSOI got into it. Basically, what happens is this lowers the power consumption and provides high speed. This FDSOI provides high speed, making it these FDSOI cells are technology comes into application where all there is automotive, RF applications, IoT applications. So this fellow is an alternative of FinFET. Okay. Yeah. What is there? Okay, so what does this topic, this FinFET and FDSOI tells us? So as an implementation engineer, as a physical design engineer, if you are trying to implement a design, these are technology that are grown by the fab. Okay, these are characterized, these are designed. All these will be readily available to you. When you are trying to implement using these standard cells, using these technology, you are just going to use it. You are not. There will not be any analysis that you are going to perform here. I mean to say, if you are using a FinFET or an FDSOI, it will be given to you as a ready-made, as in the library cells and all. As part of library cells, it will be given to you. Yeah. So then, but on the process, depending on the process, you will have the difference only at the physical verification step. Okay. So yeah, we will have more detail about FinFET in tomorrow's session. Now I actually want to cover for tomorrow's exam then some important topics. Okay, and I'll give you a few suggestions also to go through a few topics. There are some level of tricky questions that I have had it. Okay, just a moment. I'm sharing, stopping to share. Yeah, to start with, see, please, I mean, any doubt until this regarding FinFET? Anything we'll be anyway covering tomorrow also. Anything you want to say? Okay, so how prepared you are for your exams tomorrow? Is the preparation going on, or you have to prepare?
It's going on, sir.
Okay.
It's going.
Okay, please prepare well. See, I am very much concerned about the marks that you score. That's because the certification and all depends on that only. So please prepare well. This is the third assessment that you are going to do, and this will it will not be like your first two assessments, because this is the actual core concepts that you have studied. Actually, for the course, this is the main concepts that are there. So the questions, I mean, most of the questions are really straightforward. Some of the questions will a little bit confuse you. It will not like it is not going to be. It is not more analytical, but it will a little bit confuse you. That's what I would say. And I have given enough time. Okay, for all the questions, I calculated each question's time and given the time also. That totally will be 20 minutes. The exam will be on 20 minutes. So you have sufficient time. But yeah, so some topics that I want to mention. Please stay focused on those topics are like the STA. Okay, static timing analysis. Any static timing analysis, do you guys have any doubt? Anything that you have, you can tell me now itself. Okay. So in static timing analysis, you will have questions on setup and hold violation. How do you fix those violations? All those things you will have questions on that. Then you will have about the PVT corner. PVT corners is the process voltage and temperature corners are there, no? For different standard for the standard cells. That is basically the different process corners involved. Okay. So on that also you will have you can expect questions. Okay. Then regarding power grid, IR drop analysis, all those, and in one, and I think I have to cover about this multi-cycle path, false path, all those things, right? So in STA, so expect questions on that also. Then you have, yeah, as I said, this power grid and IR drop analysis, all those things. Then yeah, CTS, LVS, DRC, those places, stay more focused on those places. Okay. Then yeah, on packaging, as I said, I've given you very little insight on package. Yeah, but whatever I have said from that, I have asked questions on that also. So I mean, just see, if you have gone through my recording seriously, I think you will be able to answer even those tricky questions that I am saying, right? In that also, you will be able to answer. Then yeah, and about the first step, that is the floor planning. Before you do floor planning, you do IO planning and all those things, right? So those things, synthesis, or I know you guys know very well about synthesis. Yeah, so that's all I wanted to say. Anything else you want to say?
Sir, do we have you formed a question on Shakti processes also? Like, should we revise that section also?
No, Shakti is just a demonstration that I have done for the class. She needs more hours to give you more insight. So I have to talk to her. So there is nothing on verification also.
Okay, sir. Thank you.
Anything else?
Sir, nearest station in IIT Madras.
I didn't get you, Jiben.
Sir, nearest railway station, because sir, I am coming from Howrah, yeah, LDP, so reservation problem.
Oh, okay. That you can just Google it up. No, even ChatGPT will tell you how to reach IIT Madras through train. It's basically the central station you have to get down, and from there you can take up an auto or there is another train also, like local train services are also there.
Sir, Chennai Central.
Sorry?
Sir, Chennai Central.
Yeah, Chennai Central.
Sir, time is exam time is 20 minutes. Question is 35. Sir, please increase exam time.
No, this is sufficient, Jiben. I have worked on this and I have given the time. This is sufficient. Whatever I have given the time is sufficient.
So there is no negative marking, though?
No, I don't give negative marking, so don't worry about it. But yeah, please score well. That's what I would say. As there is no negative marking, there is no subjective type questions. There are all objective type questions. So yeah. Anyone else? Okay.
Sir, one thing.
Yeah.
Floor planning topic, we doing one problem for finding area combination. Like that problem will be that type of problematic questions is in exam.
I will not say all those things. you are very clever, Ramya.
Sir.
Yeah.
Sir, TCL is presenting a difficult.
No, I'm not getting you. Jiben, come again.
Sir, TCL. TCL में हमारा बहुत सा प्रॉब्लम है.
ठीक है.
इसलिए बोल रहा था TCL में.
नहीं, अभी TCL में एग्जाम पे नहीं पूछा. मैं आपको अभी तक सिखाया भी नहीं ना TCL. I have to teach you, no TCL. Very good mark from Jiben Roy. Please prepare well. ठीक है.
Okay, sir. Thank you, sir.
Yeah. Okay. So if there is nothing else, maybe we can convince tomorrow just 5 minutes more. Yeah, tell me. Somebody wants to say.
Sir, Tejas.
Yeah, Tejas.
Sir, doubt taken, sir. Like,
Sure.
sir.
Regarding?
Project Pati.
I'll talk to you.
Okay, sir.
Yeah. Okay then. Okay then we'll all the best for tomorrow's exam. Anyway, tomorrow morning I have session, right? So I'll give another all the best tomorrow morning. Yeah. See you guys. See you tomorrow morning.
Thank you, sir.
Thank you, sir.
Thank you, Smita. Thank you. Thank you, Rohan.
Thank you, sir.
Thank you. Thank you,
you, sir.
Vishwajit. Thank you. Physics. Recording. Okay. So hello everyone. So hello everyone. So today what we will see is I wanted to basically show you some exploration on a particular PDK. As in there is one PDK that is provided by Synopsys itself for education purpose that has major aspects of the real PDKs that you work on. Okay, so that I'll show you what all is there in that PDK with respect to that whatever we were seeing about the operating voltage, threshold voltage, everything, whatever is there, I will try to show. Okay, one is that, and second is one topic that that is not part of the syllabus, but that is, I mean, more important is the electrostatic discharge, ESD, that we have to actually wanted to give it to you. Okay, so we'll see that ESD also. These are the two things that I want to cover today, and use some PDKs. Those are free. Okay, and it's available if you have some if you have set of Synopsys tools. They offer free PDKs. You can download and you can explore for somebody to start doing digital design. They offer PDKs. In that, they offer 14 nanometer PDK and a 32 nanometer PDK. So wanted to show you, if possible, both the PDKs. So let's start with 14 nanometer PDK. So if you just open the PDK, you are able to see multiple directories, right? Multiple folder. In this, as the name says, as the name of the folder by itself says, you could see SLVT, RVT, LVT, HVTs. Okay, these are the different threshold voltages and the corresponding library and associated files inside this directory. Okay, so I was telling you about SVT, HVT, and RVT, right? That's what I was telling when I was teaching you. That is what I was saying. Sorry, LVT, SVT, and HVT. That is what I was saying. So where that implies L as in low VT, S is standard VT, and H is high VT. But if you see this PDK, it says SLVT, HVT, LVT, RVT. So SLVT is low VT, RVT is regular VT, LVT is low VT, and HVT is high VT. Okay. So this is the most worst case. SLVT is the very least threshold voltage worst case. You will have high performance here because the VT is very less, very low. Okay. And if you see other directories, it says this is SAED 14 nanometer means Synopsys. It's the Synopsys terms. Okay. This FC says this is flip chip and this is wire bound. So if you are going to use IO pad cells, right? So you'll have to pick it up from these two directories. You'll have to pick it up. If you're going to use flip chip, then corresponding cells has to be taken. Or if you are going to use IO wire bound design, where the IO cells will be on the periphery, then you will have to use this. So IO is IO, and IO means the IO cells, IO underscore FC, IO underscore WB. These are the standard cells, standard HVT, standard LVT, standard RVT, standard SLVT. Okay, these are macros, SRAMs. Okay, SRAMs PDK, where this will have comprises of the library components and Verilog models of these SRAMs will be there. Okay, and this is PLL. PLL is phase lock loop, where if you want your design to work more than 100 megahertz, then you will not be able to send that clock from the externally. You cannot generate more than 100 megahertz. If you want to work more than 100 megahertz internally in the chip, you should have a PLL. So the PLL takes a reference clock from outside the chip, and the PLL generates a higher frequency clock, say from 1 gigahertz to 3 gigahertz. The PLL takes care of generating the clock. So if you are going to use a PLL inside your design, you can pick it from here. And these are certain associated documents for the PDK, which is the first step. Whenever you are put into a project, the first step that you have to go through is reading this document. Okay, reading all the documents, then you will have to explore other directories. These are this is the one leftover directory as in folder. Okay, this is one leftover directory which says tech data. Tech data are like the number of metal layers that are used inside, the number of metal layers that you can use for signal routing and power routing. about those informations and other files also will be there inside this. Okay. Any doubt until now? This says about the PLL. This particular file says about the PLL. This says about the IO pads, flip chip IO pad, and wire bound IO pads. This document says about the RVT, RVT library components. And this is the typical corner, RVT typical corner. And here you have similar set of files where it says this is called RVT CG is called. So usually the document will have revisions. Okay, this revision always happens whenever you're working on a project, right? Sometimes during the project itself, you have multiple releases, different drive strength. Okay. Then also it says besides the library contains all the cells which are required for different styles of low power, multi voltage, power gating, clock gating, multi threshold, etc. designs with different core voltage to minimize dynamic and so yeah, this is one thing. And there is, I mean, operating voltage is 0.8 volt and the operating temperature is 125 degrees Celsius. Okay. Similarly, yeah, you can see, so this is low corner and then you have the fast corner. So then, and these are low voltage PVT corner, that is. So it is like you have two different blocks, right? Separate.
Like if you make it to 125 degree, but we are making it 25 degree, it should have some like.
I mean, what does that mean is you have, yeah, these are all the sets. Say if you see here, types of cells that are available. Okay, if you see base are all the cells that are like. MCCS is composite current source models and NDM is nonlinear delay models. So these are two different. I mean, the concept is you will have different library. You will have the library cells that are characterized in two different methods. That is what is. But you have dot clips in both the models. NDM as well as CCS. You have composite current source modeling technology. Will be applied for category to meet the. I mean that says that you have only NDMs. Yeah, this says about the physical structure of the standard cell. Okay. Cells that are available. Okay. If you see, they are mentioning that there are 953 cells in each library, like each for each HU. Like that, it says that register. So that's why the star is mentioned here. Okay, and then you have the AND gates, 2-input AND gate. Then you have a 2-input AND gate where A is inverted input. Then you. So what is ECO2 IP AND gate? Okay, I'll tell you about ECO. So Dhanush is asking that what is ECO2 input AND gate? Okay, so ECO is meant for engineering changing order, where these are. There will be changes in my implementation which will result me to not meet the deadline for the ECO cells. That is the purpose. So when you want to accommodate certain small amount of design, so these are the cells that are available. Okay, I'm just browse. I mean, just rolling it. Triggered, POSIX triggered. Then you have filler cells. Yeah, filler cells I will take you separately. I'll talk about this separately. Yeah, retention flip flops, scan D flip flops. See, you have, if you see, you have some this setup. For that itself. So that's why if you remember, I told during the initial classes when I was talking about PDK, if you get a PDK, it will take 1 week of time for you to digest those PDKs, what is there as part of this PDK. To digest itself, it will take 1 week of time. So, but that is a necessary step. You should know what is there given to you. Then only you will be able to. Okay.
Sir.
Yeah, Jiban.
Sir, please, previous question. Sir, here star mark define this star mark define
this star is signifies that, and this star signifies from here. Is that okay, Jiban? Right?
Yes, sir.
Hi. Hello. Hi. Am you able to hear me?
Yes, sir.
Sorry, there is a power outage here. My connection got dropped. Just a minute. So you're able to see my screen, right? GDS is the layout view of all the cells and all the macros, IOs, everything that I told you about is left, right? It's called library exchange format. Then you have a directory called Milky Way. So see, these are directories as part of this particular PDK. And if you ask me whether this will be common for all the technology PDK, no, you will have plus and minus of these directories will be there. But you are done in you have done an implementation, you want to save the implementation. Okay, then you have the netlist. Netlist is you have the 1 minute. And then yeah, this is a very package. This is about again DRC and LVS, and it says in the netlist you need these Verilog models because those components in the netlist which uses the standard cells and all will need some reference, right? So those references will be picked up from this models. Okay. Yeah, so it says here, right? Because see, when you are you tell me anyone can tell me will this retention cells will be is that part of our implementation only, right? When you're doing physical design, those will be not part of your RTL, the actual design.
Yes, sir.
So when you are putting it that way, then you are is that clear or? Filler cell, I think I have not told you about this. See, filler cells are cells that are used. Yeah, that's all. Yeah, just one in this HVT cell. Inside one HVT. So if you see here, you can't open this file. This is not a readable file. You need to.
Sir, like, can we do can we run the same EDK like which is similar EDK in this thing, Cadence?
No, this is not working in this. It's just taking some time on that. So let's move on. This is like let it open. When it opens, I'll come to you. So you have the GDS, then you have the left. This left you can open and read. This is the dimensions of that layers. Okay, so yeah, these are some of the physical size geometrical and different voltages. Okay, you can see in the naming convention itself. You can see these. Library, what is it has, what of information it has. So as you say, all the time. Libraries, and the pins and its corresponding directions. Database like Milky Way, you have this .ndms. Rule file inside this will be header file, rule header file. I'm just finding that. Summary. It will define the module name is for this big is the file. So you'll have information. This big is the file. So you'll have information about doubts. If you have anything, let me know. See you in the next class. All the best for your exams. Do well. Do well. Okay. If anybody has any doubts, you can stay. Others can leave. Thank you. Others can leave. Thank you.
Could you share the document that you have presented today?
The document is part of the PDK, so I think I cannot give you that. But yeah, if you